Good morning, students. Myself, Vaidhi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject Analog IC Design for the 6th semester ECE student. The video lecture is from the topic High Frequency and Noise Characteristics of Amplifiers, which is available in the Unit 2 of Analog IC Design. In this session, we will study how amplifier gain changes with frequency and how different amplifier configurations behave at high frequencies. We will also discuss the major noise sources present in amplifiers and compare the noise performance of common source, common gate and source follower configurations. In the next slide, we are going to discuss about amplifier frequency response. An amplifier does not provide the same gain at all frequencies. The gain remains relatively constant only with a specific frequency range called the midband region. The lower cutoff frequency represented by F1 marks the beginning of the useful frequency range. The upper cutoff frequency represented by F2 marks the end of this range. Outside these limits, the gain decreases due to coupling capacitors, bypass capacitors, parasitic capacitances, and transistor limitations. The difference between F2 and F1 is called the bandwidth of the amplifier. Bandwidth is one of the most important specifications in amplifier design. Next, we see about the frequency response of common source amplifier. The common source amplifier is widely used because it provides high voltage gain. The midband gain depends on the transconductance GM and drain resistance RD. At low frequencies, coupling capacitors influence the response and determine the lower cutoff frequency. At high frequencies, the Miller effect becomes dominant. The gain drain capacitance is multiplied by the gain, creating a much larger effective capacitance. As a result, the upper cutoff frequency decreases significantly, limiting the bandwidth of the common source amplifier. Next, we see about the frequency response of common gate amplifier. The common gate amplifier offers better high frequency performance than the common source amplifier. One major advantage is the absence of Miller effect. Since the input is applied at the source terminal, the gate drain capacitance is not multiplied. Because of this, the common gate amplifier achieves a much wider bandwidth and a higher cutoff frequency. Its input impedance is approximately equal to the 1 divided by GM, making it suitable for low impedance signal sources and RF applications. Next, we see about the frequency response of the source follower. The source follower is also called the common drain amplifier, has a voltage gain close to the unity. Although it does not provide voltage amplification, it offers excellent buffering capability. Because there is no Miller effect and the output impedance is very low. The source follower provides the widest bandwidth among these three amplifier configurations. It is commonly used for impedance matching and driving low impedance loads. Next, we see about the noise sources in amplifiers. Noise is an unwanted electrical signal that affects amplifier performance. The first type is the thermal noise. It is caused by random motion of charge carriers in resistive components. It exists across all frequencies and is often called white noise. The second type is the flicker noise. It is also known as 1 over F noise. It becomes significant at low frequencies and is common in MOSFET devices. The third type is short noise, which arises from the discrete movement of charge carriers across semiconductor junctions. Noise figure is a parameter used to measure how much an amplifier degrades the signal to noise ratio. Next, we see about the noise in common source amplifier. The common source amplifier experiences several noise sources. Channel thermal noise is usually the dominant source and originates from carrier motion within the MOSFET channel. Gate resistance also contributes thermal noise, especially at radio frequencies. Flicker noise becomes important at low frequencies due to interface traps in the MOS transistor. Another challenge is the Miller effect, which increases the effective input capacitance and broadens the noise bandwidth. As a result, the common source amplifier provides high gain but may suffer from increased noise in wideband applications. Next we see about the noise in common gate amplifier. The common gate amplifier generally exhibits better noise performance at high frequencies. Its low input impedance limits the noise voltage developed at the input terminal. The effect of flicker noise is also reduced compared to the common source configuration. Thermal noise from the source resistance and transistor channel remains the primary noise contributor. Due to its low noise figure and wide bandwidth, the common gate amplifier is commonly used as low noise amplifier or LNA in RF receiver front ends. Next we see about the noise in source follower circuits. The source follower has a voltage gain close to 1, which means input referred noise is directly transferred to the output. The thermal noise and flicker noise appears at the output with very little attenuation. However, the source follower offers excellent linearity and low distortion. It is frequently used as a buffer stage in sensor interfaces, analog to digital converters, and measurement systems. Finally, we came to the summary of this lecture. Let us summarize the characteristics of the three amplifier configurations. The common source amplifier provides high gain but suffers from Miller effect limitations and moderate noise performance. The common gate amplifier offers wide bandwidth, low noise figure, and excellent RF performance. The source follower provides unity gain, very wide bandwidth, and excellent buffering capability. In practical integrated circuit design, engineers often combine common source and common gate stages in a cascade configuration to achieve both high gain and wide bandwidth. Selecting the proper amplifier topology depends on the application's gain, bandwidth, and noise requirements. Thank you for listening. In this lecture, we discussed the frequency response and noise characteristics of common source, common gate, and common follower amplifiers. Hope you all understood my video lecture. See you in the next video. Thank you.